Good afternoon, everyone. I, Tina Gurnani from ETTelecom, welcome you all to ETTelecom's webinar today. To present this webinar, I welcome Mr. Jitendra Balakrishnan, CTO of Connectivity Solutions at STL, and Mr. Alok Chandra, Head of Marketing and Brand at STL. Jitendra will be presenting and discussing the topic budgeting your link losses still. Optimize your network ownership cost. And Alok will help us moderate the session today. There will be a presentation on the topic followed by a question and answer session wherein you may submit your text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the question and answer session at the end of the presentation. Now I request Mr. Alok Chandra to take this session forward. Over to you, Alok.
Thank you so much, Tina. It's indeed a pleasure to join today. Thank you, everyone, for joining this webinar named Budgeting Your Link Losses Still, Innovations for Enhanced Network Performance. We have Dr. Jitendra Balakrishnan, who is the CTO for Connectivity Solutions at STL, who will take us through the webinar deck. Like Tina said, we'll have Q&A at the end of the webinar, and we'll also be taking questions on our social media handles. So during this entire time, if you have questions, please feel free to either drop them in the question and answer dialog box that you see on the screen. Else you could send them over to our Twitter or LinkedIn using the hashtag STLwebinar. Before we begin, I guess we have a small poll. So we'll quickly get to the poll, and then from there we'll go and Jitendra can take it over. So I guess you can see the poll on your screens now. The question is, your optical fiber choice most certainly impacts what? So you have to select one of the following options that you see. Either it is optical power budget, network deployment time, network ownership cost, or all of the above. I'll repeat, the question is, your optical fiber choice most certainly impacts one of the following. It's either optical power budget, network deployment time, network ownership cost, or all of the above. So we're going to wait for about 10 or 15 more seconds, Jitendra, and then we'll see the poll results. What do you think? How are people going to respond to this?
Well, I certainly hope we're going to get a high degree of convergence on the answer.
Okay. Okay, great. So clearly 79% of the people have voted for all of the above. So I guess that's a good starting point for Jitendra, for you to take us over this very interesting webinar. So over to you now.
Thanks, Alok. Well, looks like my job is half done with that. Thanks all for joining. We're excited to have you here. We are excited to tell you about what we have been working on, what we have learned from our experience at STL in developing passive connectivity products and deploying networks and building the networks of tomorrow. So we're going to be talking about the innovations that we are seeing and we have been part of for enhancing network performance. And we're going to be talking about something that is directly relevant to the poll questions themselves. So let us begin by looking at where we are today in the world. What is familiar to every one of us in the last decade is that consumer-led use cases, you see a lot of familiar logos over there, have led to an explosion in data. We access data on the go every day at all times from a multitude of devices, and we are only scratching the surface because once we actually get into the enterprise-led use cases, IoT and AI are two buzzwords that we hear a lot of, connected cars represented there. When you get into this set of use cases, the data requirements are going to be many-fold of what we are seeing today, and all of this is we are seeing an exponential growth in data. In fact, what we are seeing is that we have roughly a doubling of global data demand every 3 years or at this point of time. In certain geographies, like India, this might actually be happening at a faster rate. But no matter what, we are seeing this extremely fast growth in data. Now, as this data, as we see this explosion in data, what we are also seeing is that the networks of tomorrow are going to have to look a little different from what we have experienced in the past. We are seeing the convergence between optical and wireless communications. We are seeing denser networks where the number of endpoints in the access layer are growing many fold. And finally, these networks are going to require a very different level of fiberization, where optical fiber begins to penetrate areas of the network where it hasn't done so before. And if you look at the transition to 5G. The latency is one great example of how this is driving the evolution of networks and contributing to every one of these three areas: convergence, densification, and fiberization. Right. With that, we'll talk a little bit about what these converged networks would look like and where the fiberization is taking place. If you took a schematic of a citywide network and you took you took the local access network starting with the NG-PON2 OLT. You have an optical distribution network in which every different aspect of the network, the front haul, the back haul, the mid haul, every one of these is changing. And we are starting to see the penetration of fiber. Now, this is a schematic, and what we're going to be focusing on today is to see how the choice of fiber and how the choice of fiber and is going to affect various different aspects of the network. Now, when we provision new networks, there are basically three areas that we need to be looking at. The first is enhancing the network performance. Right? So we have a power budget for our optical networks, and this has to be optimized throughout its lifetime. And we'll get into that in a little bit more detail. The second one is the total cost of ownership of your network across its lifetime, both in terms of the CapEx and the OpEx that you're putting in. And the last one, which is going to be critical as we roll out 5G and we lead to the fiberization, is that these networks need to be deployed at a very different rate with a much higher reliability during deployment. So let's take a closer look into every one of these, starting with the network performance. Right. So the first thing that we have to address is where losses come from in a network. Now, as we deploy networks, what we see is that when we get further and further towards the last mile, we see an increasing number of bends and turns, and macro band loss in optical fiber becomes a very critical issue. Now, what we've demonstrated what we've shown in the figure on the right is what happens to standard single mode G.652D legacy fiber. When we look at this at different wavelengths, and we consider a turn in the fiber at two different radii. 7.5 millimeters is typical. 10 millimeters is another standard which is used. But at 7.5 millimeters, what we start seeing is that as we move to higher and higher wavelengths, we see the bend losses increasing tremendously. Now, when we're using a GPON network, taking that as the base, and we have moved from there to a 10 GPON, we see about a 3x increase in the bend loss. And similarly, if we have to go to a 40G PON network, that will be even higher bend loss. And what this is telling us is that the wavelengths of tomorrow, the networks of tomorrow, are going to be facing this macro band loss at a much higher rate than anything that we have seen so far. And we need to take this into account when designing a fiber for the network that we are going to deploy. Here's data from some field studies that we have actually conducted on this exact area, and this has been done for a long distance route, and we are talking about G.652D fiber at 1625 nanometers. And what we see from this is that we suffer an average macro band loss of around 1 dB per turn, or on 1 dB per incident of macro band. This is actually a pretty significant loss, and it has a lot of implications on your network, as we'll see in the next few slides. And what we like, this is just more data substantiating it, saying that we have multiple sources of these bend losses. Typically, when we're putting in junction boxes, tapping, fiber cuts is another big source of these. Just field studies that we have done in long distance access networks show that this is actually a very, very significant problem, especially in a geography like India. All right, so getting into the factors that lead to macroband losses, let's break up the network into three different segments: the feeder network, the distribution, and the last mile. In each of these areas, we see that band losses contribute because of various different factors. In the first two areas, the feeder and the distribution network, what we see is that we have issues of splicing, of fiber cuts, of accidental bends, either because of unskilled installation or other reasons. We have splitter losses and bend losses coming in again in the distribution networks. In the last mile, it's a little bit of a different story. But again, this is, you see bend being a very consistent contributor across every different aspect of this network. Right. And just to give you an idea as to how much a single macroband instance will contribute to the overall loss budget of the overall power budget of the fiber, what we have shown over here is that across the network, we've broken up the contributions from different sources of loss: the fiber attenuation itself, losses due to splices, due to connectors, due to splitters, and due to accidental bends. Now, if you take a GPON network, which has a 28 dB budget, what we see is that we are operating pretty close to the power budget, and just a single instance of an accidental bend might put us above the power budget. Now, the situation is very similar for an NGPON, which has a 32 dB power budget, and this is all using G.652D fiber. Now, the reason why this happens is that G.652D is very, very susceptible to macroband loss. The construction of the fiber does not include the trenches that are typically present that limit your attenuation losses due to macroband terms. And as a result, you very, very quickly put the network outside of this power budget, and you have a failed network. These accidental bends can come from a number of different sources. For example, fiber cuts. What we see today is that we have a very, very dynamic infrastructure landscape in cities where you have a multitude of services being rolled out, road construction, utilities being laid down. Any one of these incidents can have a fiber cut, and this is unfortunately an all too common scenario in India and many similar geographies. Another source of these accidental bends is the fact that we have extremely tight schedules for rollout, and the manpower that we have may not have the level of training that's needed to deploy these networks with the level of sophistication needed. All in all, G.652D fiber, the standard signal mode, is not a good choice for these networks as we get into NGPON, and we'll see a little bit more data on that. Now, just as a matter of contrast, would like to show you what happens when we put in a fiber like G.657A2, which is a bend-insensitive fiber. Now, what we have shown over here is that every aspect of that loss tree is exactly the same, except for the accidental bend. G.652D is much more forgiving, and what we see over here is that the loss due to a bend is about 1/7 to 1/10 of that of G.652D. And now what this does is that you can have multiple bends and still stay within your power budget. What this means is that your network is far more reliable and stays up for a longer time. It actually can tolerate fiber cuts. It can tolerate rollout by, say, unskilled installers, relatively speaking. In general, this is a much better fiber when we're talking about the reliability of your network. Right? So now, having touched upon network performance, let's talk about cost. Now, G.652D fiber has been the workhorse of the telecom industry for 3 decades now. But it does have its limitations. What we're showing here is the PON reach and what power budget is needed at different reaches. Now, what we can see is that from the central office, with a power budget of 28 dB, we can get to about 11 kilometers with the G.652D fiber. But that's today. Once we actually move to an NG-PON scenario with a 32 dB budget, we actually reduce that reach significantly to about 7 kilometers, which is about 50% of the coverage that we had for PON networks. Right? This is in general going to be true no matter what fiber you use, and this is actually one of the arguments that we see commonly for the need for increased fiberization. But the real comparison is what happens when we use a bend-insensitive fiber like a G.67A2. Now, A2, because of the fact that it can tolerate bend losses, can actually get to a much, has an enhanced reach. What we see over here is that in comparison to G.652D, even at 11 kilometers, we have an acceptable cushion. And we can use that cushion one of multiple ways. We can either tolerate further bends, or we can extend the reach of the network. Now, this is true even after we move to NG-PON technologies, where we still have an enhanced reach of G.657.2, typically A2 compared to D, typically about twice the reach. Just looking at these schematics, it makes it quite evident what the impact of bend-insensitive fiber is on the reach of the network. What this means is that the capex investment is very different when you choose to use G.657A2 versus D. The bend-insensitive fiber is far greater value for the capital investments that we make in networks. Now, let's talk about operating expenses. Now, what we see over here is a breakup of the power budget based on a number of different factors. This is the same data that you saw earlier, just budgeted in a different graphical form. We are still talking about losses due to fiber attenuation, splitters, connectors, and splices, and macroband losses in yellow. Now, on the left, you see G.652.D, standard single mode low attenuation fiber. Now, what happens is that because the macroband losses are significant, we don't leave ourselves much room for repair. Typically, 6 to 7 is our estimate based on our studies at Sterlite. However, when we add bend insensitivity to the low attenuation, which is essentially a G.657.82, what we see is that the macroband losses go down so significantly that it tolerates more than double the number of repairs or cuts that we typically do. What this means is that your network stays up for longer because it's the same rate of cuts per year, and we estimate that it can add around 10 years of increased network life because of the added ability to tolerate cuts and the macroband losses that come with it. So there's yet another advantage to bend-insensitive fiber. Now, when we look at cable design, this is where the bend insensitivity begins to matter a lot, and this is because of microbending. Earlier, we talked about macrobending, but here's where we talk about microbending, which is a very different phenomenon. It's completely prevalent when we start moving into tighter and tighter cable designs. For example, when we move from a loose tube cable design to a micromodule cable design, there's a lot of stress on the fiber and it undergoes a lot of microbending, and we see an increase in attenuation because of the microbend performance. Now, G.652D fiber cannot tolerate these kinds of tight cable designs. We've shown some schematics over here. And what we know is that we can actually pack in a whole lot more fiber than we typically do in loose tubes, but we can only do that for the right kind of fiber. Now, what you see on the table on the right is showing you what happens at a particular microduct size. Now, when we deploy these cables, either by blowing or pulling through a microduct of, say, 16 millimeter OD, 13 millimeter ID, if you want to pack in as much fiber as we want into this, we basically can put in about 192 fibers in a loose tube. On the other hand, this number can go up dramatically to about 432 fibers when we actually use G.65782, simply because of its ability to be cabled into tighter and tighter footprints. Now, this automatically means that your capex per fiber installed is quite different than what we would see with A2, and it enables the fiberization, the deep fiberization of networks. All right, so we talked about network ownership costs. We talked about capital. We talked about operating costs. And the last area that we need to talk about is network provisioning. So when we're talking about network provisioning, the first thing we'd like to start off again is a cost-related item. But it also talks about the rate at which we deploy networks. Now, why do we want to deploy networks faster? There are two reasons. One is that the cost of network creation is significantly lower with faster deployment, and that's what's shown in the bottom half of that graph. When we move to faster network deployments, which is shown in the curve in blue, as opposed to the original schedule that we might have had in black, the shaded region is a pictorial representation of how much cost you save through faster deployment. Now, the other thing that happens is on the revenue front. When you deploy your networks faster, you begin to capture an incremental market share, possibly through an early mover advantage. Your subscriber base could increase, and in a really tight market scenario, what happens is that you end up with a higher revenue, a lower cost, and obviously a very attractive proposition for any network provider, enabled by the fact that you're choosing the right fiber. So, touching upon the cable aspect of it again, the cables actually we talked about the footprint of the cables, but the other aspect that we need to talk about is how we deploy these cables. What is the preparation that is needed when you terminate these cables, or what is the midspan access that you have? Again, without going into too much detail about in this graph, what we have seen is that the joint splicing of cables it takes a very, very long time. And what's shown over here is typically the way an installer spends a lot of time at different aspects, whether it's a mini loose tube or a loose tube, and whether it's the preparation at the end or not. Now, all of this is something which can be significantly improved with bend-insensitive fibers. These fibers are extremely tolerant of abuse and being put into much more of a harsher handling environment than legacy fiber, which is D. So what we see over here is that we could have an average 40% reduction in installation time. This is one of the reasons why networks can get provisioned much faster with G.65782 bend-insensitive fiber. So now, one of the things that we have to look at is that let's just take a step back. What we have talked about so far is that the advantages of bend-insensitive fiber. We have demonstrated how the network performance increases quite significantly when we consider the power budget when using bend-insensitive fiber as opposed to standard single mode. We talked about the ways in which the network ownership costs can be reduced significantly using bend-insensitive fiber. And finally, we talked about faster network provisioning using bend-insensitive fiber. There's a very, very clear advantage that we have seen in all our studies, all our field trials that G.65782 fibers have. But that's not the whole story. There is a very big challenge that exists. It's simply that G.652D and G.65782 have different mode field diameters, and the mode field diameter mismatch is a very significant issue. Now, shown over here is a schematic. Typically, you have G.652D fiber, which has an MFD of 9.1 microns at 1310 nanometers. The comparable figure for G.657A2 bend-insensitive fiber is 8.6 microns. You typically have about a half a micron difference between the mode field diameters. Now, why does this matter? Well, let's take a look at the splicing of these two fibers with each other. When we splice two fibers with different mode field diameters, the results show up in the OTDR reading when after we do the splicing. Now, in the figure on the left, what we see is a plot of the power loss versus the mode field diameter mismatch. So the number on the x-axis represents the delta between the two mode field diameters. And in the case of a D versus A2, you'd be roughly in the 0.4 to 0.6 range, which are the two regions in the circles. Now, why are there two different curves over here? The answer is that when we go from a fiber with a lower mode field diameter to a higher mode field diameter, you see an apparent gain in the splice loss, which is completely which sounds completely out of whack if you've been used to splicing fibers with the same mode field diameter before. On the other hand, when you go from D to A1 or a higher mode field diameter to lower mode field diameter, you see an apparent loss. Now, this is all in a unidirectional OTDR measurement, and the numbers are shown in the table on the left. When we look at the column, the second column, which shows a D to A2, you see a splice loss and quite a significant deviation from what is an acceptable reading of typically 0.1 dB. But on the other hand, if you actually looked at a unidirectional OTDR from the other side, you'd see a splice loss which shows an apparent gain. It's shown as negative because it's a loss over here. Now, the way to solve this is to do a bidirectional OTDR, and which you took the average of these two, and it would give you the actual real splice loss. Now, but this creates a problem. When you're an installer in the field, that's not the world that you live in. Right? So here is an example of what an installer sees. On the figure on the left is exactly the same as what you've seen before. And the figure on the right is the image that an installer sees while provisioning the network. Now, when you have these two fibers, what you see on the left is the it's a D fiber, and what you see on the right is the A2 fiber with a slightly lower mode field diameter. And you see that splice joint, you see a very thin line on the screen of your on the screen when you actually are putting the splice in. And although the estimated loss is fine, that's actually a red flag for an installer. They have to go back, prepare the fibers again, make the fibers spliced again, but it's never going to go away. And often this creates a little bit of confusion over the splicing and the fiber quality aspects of what's happening. Now, the unidirectional OTDR is never going to get away from this. The way in which we can solve this is bidirectional OTDR, but that is extremely cumbersome for an installer. If they could help it, they would like to stick to a unidirectional OTDR measurement and make sure that they're getting a good splice the first time, every time. Now, if we had to solve, what we have talked about is two different aspects to this problem. We talked about bend insensitivity first, and now we talked about the mode field diameter mismatch, which creates a big problem in the installer's mind. From an optical physicist perspective, this may not be a very big deal, but that doesn't help when you're actually deploying the networks, because you have to look at it from the perspective of the customer. That's exactly what we did. We combined both of these aspects into one product, which can give us multiple applications and bring in the best of both worlds. We achieved what we think is the right balance. And we would like to introduce to you Stellar, the new fiber that we have created. What it does is it combines the best-in-class attenuation with bend insensitivity. Now, when you compare Stellar with G.657A2 fiber or Bolite, as we refer to it in our brand name, or when we compare it to G.652D, which is OH Lite Nova, what you see is that those attributes combine beautifully. It has the loss of the low attenuation fibers like OH Lite, typically 0.33 dB per kilometer at 1310, 0.19 at 1550. And it also has the MFD of a G.652D fiber, which is 9.1 microns. However, the macro band losses are exactly the way the A2 fiber behaves. It's less than 0.1 dB per kilometer at a 10 millimeter radius for one turn. And when you put both of these together, what you have is the benefits of bend insensitivity with the compatibility to legacy networks. Right? And you see that bend insensitivity when you compare on the figure on the right, when you compare it to G.652D or an enhanced fiber or an A1 fiber like OHLF Nova versus Stellar. It's about 10 times lower than A1 fiber or about 40 times lower than standard single mode. Now, when you put these together, Stellar begins to find application in every aspect of the network. It can be used for future ready networks with next gen cabling. It can handle the power budgets like we showed for when we transition from NG-PON to NG-PON 2 and so on. And it pretty much can handle anything that you can throw at it at this point of time. So this fiber is first in class, and we are extremely proud to bring this to you. And we believe that this fiber is going to enable the networks of tomorrow. So with that, I'll hand it back to Alok and talk about STL as a whole. Alok, do you want to take it from here?
Yeah, thank you so much, Jitendra. It was fabulous the way you have actually taken us the entire deck. Before we go to the next section, I'd like to quickly invite you to ask questions if you have. During this entire time, you can either push the questions through the window that you have, else you could also tweet us or send us questions via social media, either on Twitter or on LinkedIn with the hashtag STL webinar. So I'll go to the next slide now. This is the slide which actually talks about STL as a company. So we would like to say that we are data networks innovator, and we have innovations going across the entire spectrum, the entire stack of layers of a data network. This entire data network innovator is run by the company STL has 3 innovation engines: connectivity solutions, network services, and network software, with 9 distinguished capabilities. These are the capabilities which are very unique to each of the innovation engines that we have. So for example, advanced photonics, material science, and precision manufacturing for the connectivity solutions business. And then we have automation and robotics and algorithmic design capabilities at network services layer or network services business, and AI analytics and web scale DevOps and programmable networks for the network software. If you go to the next slide, Jitendra, this is about us, STL, in numbers. Well, in terms of customers, we have about, we work with 8 of top 10 telcos globally. We're working with top 2 cloud companies, and we have operations in more than 100 countries. As well as today. In terms of innovation, we have about 4, distinguished innovation centers. We have seen a tremendous, increase in our patent filing. Staggering 103% 5 years compound annual growth rate, especially for the optical fiber cable patents that we see in the entire portfolio. We have global footprint. STL has production facilities spread across continents. We have in total about 7 global production facilities and nearly 50 million fiber kilometer fiber capacity. With that, I'd like to move to the next slide. With this Stellar Fiber launch, we are going to be demonstrating this, and we're going to be launching this in full glory at the India Mobile Congress, the event which takes place from 14th to 16th of October. We're going to be at hall number 4 in New Delhi at Aero City. So I guess with that, we have reached to the end of the presentation. If you go to the next slide, Jitendra, I think this is just a recap of what we have been saying. In case you have questions, we can take them right now. or you could also send in your questions with the hashtag STL webinar, and we'll be taking them at the end of the webinar as well. So if let's quickly see what kind of questions do we have at the moment. So Jitendra, so one of the comments that we have and a question, it says, great presentation. Can you please explain what is the proportionate change in the cost of electronics when they lay out new cables? I'll repeat, can you please explain what is the proportionate change in the cost of electronics when it layout of new cables, when new cables are laid out?
Let me make sure I understand the question correctly. If the question is what is the cost of new electronics when we deploy new cables, let's distinguish a couple of things. The cost of electronics is heavily dependent on the choice of what kind of network you're running. For example, NG-PON, NG-PON2. The cables that we deploy may or may not be connected to these choices. As an example, we talked about tighter cable. So the cable designs, obviously, the densification is enabled. Enables future networks, but the electronics is basically a slightly it's a slightly different choice. Now, what we can say is that we have a reduced cost of deployment, right? And we can use and the B class optics that we're using at 28 dB and versus what we're using at 32 dB, we actually have the 28 dB. It's cheaper than what we can use at 32 dB, but that's again because of the choice of network. These are two aspects which are not directly cause and effect, but they have the same. They have the basis on the choices that we're making based on the network. So in summary, I would say that your electronics choice depends on what kind of network you're running, and your cable choice also depends on what kind of network you're running. And that's the way in which they connect it, but it doesn't directly link up one-on-one. I hope that answers the question.
Yeah, I hope that answers the question. We have more questions coming in. So the other one is, can a single fiber be used for all network sections, whether it's core, metro, or access?
Well, until today, my answer would have been no, because as we get towards the last mile, we need bend insensitivity. However, when we using bend insensitivity as bend insensitive fiber, we see the mode field diameter mismatch, and a lot of places the installers are very resistant to using those fibers, and so you had these two aspects going against each other. Now with Stellar, we are pretty confident in saying that we can use the single fiber across all aspects of the network, and this is, to our knowledge, a first in its kind, where we are using the same fiber in access networks, in last mile networks, and so on. With Stellar, I think the answer to that question becomes yes. You can use the same fiber in every aspect of every part of your network.
Okay, great. I hope that answers your question. The next question is, what would be the innovative ways to minimize the splicing losses?
Innovative ways in minimizing splicing losses. Okay, this is actually a question which can take you very, very far down the rabbit hole.
Conceptual question.
So splicing technologies are increasing in their sophistication year after year. So there's a whole area of that, obviously. The area that we have actually chosen to focus on is to make the life of a splicer as easy as possible when they're deploying a network. Right, so rather than focusing on the advances in splicing technology, which are going to be common to any fiber that we are using, and so on, let's talk about the aspects which cannot be fixed no matter how good your splicing is, which is basically the mode field diameter mismatch. Right, so the innovative approach over here that we have chosen to focus on is basically matching the mode field diameter and making sure that your splice happens to be right the first time, in like with the simplest possible equipment, using unidirectional OTDR, an installer can actually tell that the splice has been done perfectly because the mode field diameter is matched. Yet the fiber that they're using to splice to a legacy network is the best in class when it comes to bend insensitivity. So this is one of the approaches that we have chosen. We think it's fairly innovative, and it solves a real-world problem from the installer's perspective, and the installers who are normally not the focus of attention turn out to be one of the most critical aspects of deploying networks faster, better, cheaper. And I think this is where Stellar really stands out.
Okay. Great. One of the next question is another very interesting one. Does higher MFD impact, or does higher MFD impact design of tighter cable? Will it have an impact on the design of tighter cable?
Does higher MFD impact the design of tighter cable? Not directly, no, because the design of tighter cable relies on bend insensitivity more than anything else. It depends on microbend performance. Now, you can have microbend performance at different MFDs, and like for example, you can create a G.65782 fiber with an 8.6 MFD with a 9.1 MFD, and they have slightly different bend performances. That's a secondary effect. The primary effect and what contributes to tighter cable designs is essentially your bend insensitivity and the way you design a trench in your fiber, the way in which you can contain the light even through tight turns. So that's what I would say is a primary aspect that we focus on as cable designers as we move to tighter and tighter cable designs, high density cables, and so on.
Okay. The next question is, high fiber count cables aren't really used in India. How do the benefits stack against such deployment scenarios in India? So there's an assumption and there's a question next to it. So the question is, how does high fiber count cables stack against such deployment scenarios in India? Or they are not necessarily used in India, is the assumption here.
Sure. Yeah. So when we talk about high fiber count cables, this term is used differently depending on application in different parts of the world. I mean, like for example, in some places you might consider a 500 plus fiber count cable to be high density, depending on its diameter. In other places, when you're talking about hyperscale data centers, you're talking about a few thousand fibers in a tight space in fiber. But let's talk about telecom applications, and let's talk about fiber counts in the 144 to 864 fiber count regime. Now, what we have seen is that yes, initially networks up until the 3G and 4G eras don't really require high fiber counts, like simply because of the demands of the backhaul. But that scenario will change very, very quickly. The question is, how much do you want to future-proof your networks? And this is where I think that it's really worth operators taking a futuristic outlook, because the fiber is the cheapest part of your network, yet it is the most critical element of your network. If you invest in fiber, then you actually are future-proofing your networks. And so while it is true that India has not had a history of deploying fiber at high fiber counts before, we think that that scenario could change as we move towards higher and higher bandwidth, towards 5G, towards future networks, and those changes could come very, very quickly. What we do know that it's inevitable. The question is when it happens, and the sooner we are ready for it, the better.
Great. We have more questions coming in, Jitendra. So really good information and presentation. How do you ensure compatibility of G652D with G657A2, especially when MFD mismatches are there at multiple locations and single span using both types of fiber in bits and pieces?
Yeah, a great question, and that's exactly the problem we think we have answered with Stellar. So what we have at Stellar is a G.657A2 fiber. It has the mode field diameter of G.652D. So you're right. That mismatch in MFD is one of the critical elements that operators and installers face a difficulty with every day. And with Stellar, we have to design a fiber specially to address this particular issue. We believe we've answered the question with the introduction of Stellar, and we definitely hope that using it in the networks will solve that particular problem where you have the MFD mismatch across different pieces of your network. Stellar should pretty much take care of that, make it compatible with legacy D fiber. It will have a mismatch with any A2 fiber which has an 8.6 MFD, but those are not very commonly deployed yet in India. And with this, we actually think that we can bring the benefits of G.657A2 into Indian networks while still retaining the compatibility with the G.652D legacy networks.
Great. The next question is, what is the average life of OFC? Also, do dark fibers also start depreciating even without usage?
Can you repeat the question, please?
What is the average life of OFC, optical fiber cable? Also, do dark fiber also start depreciating even without usage?
Okay, let me answer the first question. What is the life of OFC? Well, typically we design cables to outlast the network lifetime by quite a bit. I mean, we actually guarantee that cables would last, for example, of 25 years, but those cables can actually carry on for much longer than that. However, your network will not last that long using those cables because they will undergo cuts, they will undergo transitions, and you will have different technologies coming out. So what we can very confidently say is that your cable is not going to be the problem. The change of technology is going to require you to redeploy your cable much before that. That's the first part of the question. The second question was that whether dark fibers depreciate over time. By this, I assume you asking whether there is a deterioration in performance of the fiber or any kind of adverse effect of the fibers over time. Now, from a physical standpoint, those fibers are no different from the fibers which have been active and lit. They will last exactly the same amount of time. So deploying them in a network and not using them right away is not going to be an issue as far as the lifetime or optical performance of the fiber is concerned. It's future-proofing your network in the sense that if you deploy twice or thrice as many fibers as you need while installation, you save on installation costs as your network starts having more and more data demands on it. You can easily use that excess capacity, and it's far cheaper to put excess fiber down than it is to go back and redeploy fiber because, like I said, the fiber and cable is actually a very, very small part of your network costs compared to everything else that you have to do, including laying down the networks. So I'm not sure whether that exactly answered the question, but I've tried to interpret that question of dark fiber and depreciation in terms of what it would mean if you deployed excess fiber and didn't use it. Would it deteriorate? Is there a downside to it? That's what I've tried to answer.
Great. Very interesting question. Please provide your views on multi-core fiber and R&D.
Multi-core fiber. So multi-core fiber has been around for a very long time, and very quickly, by way of explanation, what we have in standard fiber is that you have a circular core, typically of around 8 microns diameter, in a 125 micron clad, which is basically true for no matter which category of fiber that you're talking about. With multi-core fiber, we arrange multiple numbers of these cores are typically still within a 125 micron clad, and this actually amplifies the light carrying capacity by the number of cores that you have. Now, there are significant disadvantages. The first is that the most critical disadvantage for multi-core fibers is that the cost of production of multi-core fibers is prohibitively expensive even today. And these fibers are pretty much found in research applications. The advantages, of course, are they can enhance your data carrying capacity by numbering up the number of cores. Right? And the other part that we have to control is the crosstalk between the cores of these fibers. Now, there have been a number of different demonstrations of multi-core fiber over the years. You have 2-core, 4-core, 7 and 8-core, all the way up to 19 cores at this point of time that has been demonstrated, and the complexity goes up by the number of cores. Now, where multi-core fiber might find its first actual real-world application deployed at scale is when it comes to reducing the cable footprint. Because, for example, if you have a 4-core fiber as opposed to a single-core fiber, you're effectively reducing your cable diameter by half. It goes as a square root of the number of cores. So you're reducing your cable footprint by half, which is actually a significant change. By doing this, as networks demand tighter and tighter cable, you might start seeing the need for multi-core fiber to transition out of the research labs into actual practical application. Hope
Great.
that answered the question.
Yeah, I hope so too. And the questions are still pouring in. We have very little time left, around less than 8 minutes. So I'll try and ask you as many questions as I can. One of the next question is there style of fiber product related details are available on STL website? Well, we'll be hosting this webinar on our website as well. And you can reach out to us. There's an official launch that'll be happening, in some time. Please hold tight for that. And we'll be, of course, launching all of the rest of the details there. Can we use G657 fiber for both long distance and local loop is the next question, Jitendra.
Can we use G.657 fiber for long distance? And what's the other one?
Local loop.
Well, we think that this fiber can be used in all parts of the network. Now, G.657 fibers have not typically been deployed in long distance networks in the past. And that's because these networks don't typically suffer macroband issues. They are, like in long-haul networks to the same extent that you do in access. However, we have actually seen through field studies in India that that may not be a good assumption. We have seen that long-haul networks too suffer fiber cuts. And you frequently see the need for macroband performance in long-haul networks. So we believe that it's really time to revisit that assumption that that bend-insensitive fibers are not needed anywhere else other than the access networks. And in fact, G.657 families of fibers have been reclassified to actually reflect the fact that they can find application beyond the initial last mile connectivity where they were designed for. So local loops, absolutely. You have to use these. You pretty much cannot use any other fiber other than bend insensitive fibers as you get closer and closer to the termination point. The challenge has always been the compatibility of mode field diameter. And again, coming back to why we think Stellar should truly live up to its name, is that it is the first fiber which you can seamlessly use from long distance networks through access networks to last mile networks, deploy the fiber with ease, and have the entire network to be compatible with each other in terms of mode field diameter and hence the rollout. Yes, so G.657 fibers can be deployed across all parts of the network, provided you have taken into account the benefits of the power budget, and you made sure that the fiber that you're deploying is going to be easy for the installer to deploy. And Stellar definitely meets those criteria.
Great. The next question is, what is good for single mode transmission of fiber with low MFD or fiber with higher MFD?
Well, so it really depends on what you mean by transmission. So like, for example, so the higher the MFD, so the launch power varies depending on what the MFD is. So there are fibers with very high MFD, which have specialized purpose. I mean, G.654E fibers are an example, in which, so typically you could have a low loss, high MFD fiber, which is used for long distance transmission, and so on. So MFD is just one of many criteria that you have to use when you're looking at when you're looking at transmission. There are a number of different other parameters, and this has actually been the reason why there are multiple different ITU classifications of fiber. So MFD is, like in the context that we have been talking about, MFD is critical in terms of making sure that your installation is right. It is one of the parameters that affects transmission, but it's not the only one. There are many others that many other aspects. It's actually a pretty wide-ranging question that we don't want to get into. I mean, like for things like chromatic dispersion, etc. That it's just going to take extremely long it'll be an extremely long and rambling answer for that question. So I'd say that just that MFD is one of many parameters that we have to consider in transmission.
Okay, great. I guess we have just about time for one more question, and then we'll have to end this presentation. So very last question I'm taking, how can we ensure last mile access also set up with protection to provide high availability at client and in case of fiber to the home? How can we ensure the last mile access also set up with protection to provide high availability at client's end in case of FTTH?
Okay, I'm not sure I follow the question completely. So, Alok, the question was that how do you ensure a last? How do you ensure?
How can we ensure the last mile access also set up with protection to provide higher availability at client's end? Basically, with a better experience to the user, better reliability, what kind of protection mechanism can you use at the last mile access? Well, I guess is a little off the topic.
So actually, I'm just going to mention how I interpret the question. I think the question is referring to the fact that as you get to last mile access, the network becomes more vulnerable to various factors, and how do you make sure that you avoid that those different vulnerabilities, for example, physical damage, going around bends and so on and so forth. So the answer to that, it might be an incomplete answer. The answer to that is that the fiber needs to be able to tolerate that abuse. For that, you need bend insensitive fiber. G.657A2 is the fiber that I would choose. The second part is that your cable construction needs to be robust enough to handle the application. For example, you have cable construction which is smaller in footprint, which can then undergo tighter routing. For example, you could have armored cable, which is resistant to various factors, like for example, rodent bites and so on and so forth, which turns out to be a common problem. So I would put the answer to do these two categories, and that is you need better fiber, and you need to worry about cable construction. And fortunately, the fiber choice that turns out to be the best for both these cases is bend insensitive fiber.
Great. With that, we are already at the top of the hour. Thank you so much, Jitendra, for this great webinar. I have a lot of questions which are still unanswered. I'd request that we continue this conversation on our LinkedIn and our Twitter platforms. You could go ahead and join us on LinkedIn and Twitter and ask questions that we have not been able to answer today with the hashtag STL webinar. With that, thank you once again, and over to you, to the ET team. Tina.
Thank you.
Thank you, Mr. Jitendra and Mr. Alok, for conducting the webinar session today with ETTelecom. Unfortunately, we won't be able to take all the questions due to time constraints. If you have any other questions, please send them at editor@ETTelecom.com. It was an engaging and insightful talk, and hope all the participants have enjoyed the session. The recording of this webinar will be made available on ETTelecom.com. Thank you everyone for joining us. Goodbye.
Thank you. Bye-bye.
Bye.